Thanks, Paul, and hello, everybody. As Paul mentioned at the beginning of his portion of the presentation, my name is Jake Selstad. I work for the Center for Energy and Environment. My title is Inspector Rater, and as it suggests, I do some quality assurance inspections, and I also do new construction energy ratings, basic HERS ratings for utility rebates, along with national certifications like Energy Star, EPA's Indoor Air Plus, Department of Energy's Zero Energy Ready Homes. I'm also a Passive House Institute US multifamily verifier. In addition to my day-to-day work, I occasionally help out our research department with any projects that they have involving air leakage testing, and that's what I'll be talking about today. The testing procedures and test results I'll be describing were just one part of a larger DOE field study looking at the impacts of changes in energy codes and how that affects real-life energy usage in multifamily buildings. As Paul mentioned earlier, this project was headed up by Ecotope in Washington with partners EcoAchievers from Illinois, Slipstream from Wisconsin, Paul's organization, Energy Conservatory, and my organization, Center for Energy and Environment, here in Minnesota. In addition to the actual leakage results, the goals for this study were to determine whether or not a relationship exists between the types of tests that can be performed in a multifamily building, how strong that relationship is, whether or not the type of building itself impacts air leakage, and what other variables might affect predictive power for energy use. We also are looking to provide an envelope air leakage protocol, provide guidance for code language, and assess the overall energy impact of air leakage testing using that protocol. There are three main tests that can be performed on a multifamily building. The first is single unit compartmentalization. This measures the total leakage of a single unit, both exterior leakage and leakage within the building. This is the easiest test to implement and the most common. The whole building test measures the leakage of the whole building and corresponds most closely to the intent of airtightness test in the IECC definition. Single unit exterior or guarded test measures just the exterior leakage of a unit. This is the most complex to implement because it requires at least two sets of blower doors. One of the goals of the study was to compare air leakage across building types. For this study, those types were common entry and garden style. The characteristics of a common entry are closed corridors and common areas, and access to the units is from interior hallways. Garden style, on the other hand, has open corridors, and access to each unit is directly from outside. Unfortunately, we were only able to test a handful of garden-style buildings, and therefore there wasn't really enough information to make a decent comparison between the two building styles. The reason for this is because it's just not as common of a building type, at least in Minnesota, and we didn't get as much participation in Washington and Oregon where this building type is more prevalent. I did want to talk about it though, because the testing procedures for testing a garden style versus common entry is quite different, basically because of the multiple and independent doors. You need a separate fan for each unit, and this can be quite a challenge. I should also note that the definition of garden style in this project did not include townhouse or row house. So although we do have quite a few of that building style in Minnesota, they didn't actually meet the definition for this project, so they were not included. This building here was one of two garden style that we tested here in Minnesota. The second building was an identical building on the same complex down in Rochester. And although this looks like a townhouse at first glance, it's actually 8 units stacked on top of each other, all with independent exterior doors, so it does meet the criteria for a garden-style building. And because this building has 16 independent sections or zones, we needed 16 fans to ensure that each zone was reaching its 50 Pascal difference for our whole building measurement. Using TechLog, we were able to control all the fans and capture all the flow measurements from one computer. Each zone was independently baselined and brought up to an independent induced 50 pascals pressure. Once at 50 pascals, each unit was guarding against each other, and then the total fan flow for all fans gives us a true measurement for exterior building leakage. If you don't have 16 blower doors, you can still get a pretty close idea of total exterior leakage for a building like this by doing repeated single unit guarded tests. For this particular building, you would need at least 4 blower doors. So imagine you're testing this unit up here. You would need to also run the unit below and left and right, also at 50 pascals, and that would give you your exterior leakage for the tested unit. You would need to repeat this test 16 times and then manually sum up each fan flow, and it would give you a rough idea of total exterior leakage. Whether you have 16 blower doors or you're using several blower doors, moving them around to do a manually guarded test, it's a lot of setup to test a building like this. Here you can see Paul setting up one of the blower doors he borrowed us for this particular test. We needed to set our blower doors up a little bit differently than you would for a standard single family test. We needed our gauges outside so that we could change configurations as needed to make sure everything was communicating with the laptop appropriately. And also because our gauges were outside, we needed to reference the house pressure as well as the pre-fan pressure, and also extended some of our exterior reference hoses so that they were not interfered with the fan flows from the adjacent units. Once we had all the fans set up and all of the gauges communicating, the testing actually went pretty smooth because we didn't need to move any equipment around. In addition to the whole building test where we were running all fans simultaneously, we did compartmentalization testing and single unit guarded testing using the already set up blower doors. For compartmentalization testing, we already had gauges set up in all adjoining units, so no matter what unit we were testing, we could measure the pressures in the adjoining units. Same for the single unit guarded. We had all the fans set up so that we could induce 50 pascals on all sides of whatever unit we were testing for exterior leakage. The next building type is called a mixed-use building. This is a variation of the common entry building. This particular building had all first floor commercial retail space and 2 floors of residential above. It still has common space and common access to all the units, but it does have mixed usage on the first floor. This is the floor plan from the building in the previous slide. We had 2 identical floors on second and third of residential space and commercial space along the entire first floor. However, not only did we need to guard this space, it was actually separate zones, so they each needed to be independently guarded, meaning there was a fan in each zone. By guarding against the first floor commercial spaces, our flow measurement at our blower door setup in this stairwell over here, which was connected to the 2 floors above, meant that flow measurement was actually just exterior leakage for the residential areas for our whole building test. We also needed to guard against the first floor commercial space for all of our single unit exterior leakage tests on the first floor to ensure we weren't measuring any leakage between the commercial space and those units. Because the protocol for this project requires new baselines for each measurement, that meant somebody had to be outside capping and uncapping each of these first floor commercial space blower doors for every measurement that we did. So that means we had to have at least 3 people, 1 person up moving the duct blaster blower door fan for the units, 1 person in the lobby running tech log, and 1 person outside in the winter all night capping and uncapping these fans. So it was quite a challenge to do a building like this. This next building was a smaller mixed-use building with only 2 zones on the first floor. You'll notice that the lobby is actually on the first floor in one of the zones that we excluded from the residential air leakage test. This was just to be consistent with the previous building where the entire first floor is excluded from residential area. On this test, we attempted to be a little bit more efficient by keeping all of our fans in a more centrally located position. This meant that we didn't use this other stairwell on the other side of the building to depressurize the residential area. We actually depressurized the residential area through the lobby. Because we still wanted the lobby to be guarded, we had another fan set up in an exterior door in the lobby area. This fan was depressurizing not only the lobby, but accounting for the pressurization coming from the residential blower door setup in the stairwell. In order to get this to work properly, we had to play around with the fan adjust rates in the cruise settings in order to get both zones to stabilize at 50 pascals. I can't remember the exact settings for this, but the key takeaway is that those fan adjust rates need to be different. To be consistent with our other testing, we did actually run a tube from our residential setup directly to outside. In this case, both north and south because it was a windy night. However, we could have actually run this blower door cruising at 0 pascal pressure with reference to the lobby, and then as the blower door setup in the lobby depressurizes that space to 50 pascals, the residential blower door would follow suit and ultimately get that residential section to 50 pascals as well. By having most of our fans set up right within the lobby, it was much easier for us to cap and uncap fans for our various baselines. However, we did still have this other separate zone to contend with. To deal with this second zone, the Energy Conservatory actually came up with a prototype automatic capping and uncapping damper for the fan. Here we can see that damper in action. You notice it's actually just a lightweight piece of plexiglass taped to the fan with a magnet in the center. So when the fan starts up, it builds up pressure and pops that open. And then when the fan turns off, the damper actually just shuts and then connects right to the center of the fan with the magnet. By having a fan that would cap and uncap itself, it really streamlined our process because we didn't need to have someone running around to each fan location to cap and uncap for each baseline measurement. Because we needed to depressurize the entire building for our individual unit leakage tests, we were essentially getting a repeat test for the whole building leakage, even when we were using these dampers. And as it turns out, our flow measurements were not that far off from an unimpeded initial measurement. So although these aren't fully calibrated, they actually don't impede the airflow too much. You'll also notice on the right here, Energy Conservatory built us a automatic damper for the duct blaster fan as well. And this one was actually quite interesting. It's a 10-inch butterfly damper mounted directly to the fan. And this one was actually calibrated and tested as accurate down to 50 CFM. So we were actually using this for our compartmentalization and unit exterior leakage measurements. The common entry building without mixed commercial space was the most often tested in this study. This particular building looks a little weird because the first floor is actually the parking garage. It's not actually underground. We did not guard against any garages in this study. Any leakage from residential to garage was considered exterior leakage. Before getting into the test results, I wanted to go over the three main tests we did on these buildings in a little bit more detail. The first test was compartmentalization, and as you remember, this test measures the entire leakage of a unit, both in and out. So therefore, most guidance suggests that adjacent unit doors are left open to relieve any pressure that may be built up in adjoining units. However, we actually wanted to see how much of a difference that makes. So our first step was to perform the compartmentalization test with adjacent unit doors shut and measure the pressure from the adjoining units to the hallway. And if that pressure changed by more than 5 pascals while we were running our compartmentalization test, we would actually open those doors for any units that would change more than 5 pascals and then repeat the test to get a second measurement. The next test is a whole building measurement. For this test, all interior doors, both unit doors and doors within the units, are open to ensure that the entire building is tested as one single zone, giving you exterior leakage for the entire building. The next test is the individual unit's exterior leakage or guarded test. As Paul described earlier, the individual unit's exterior leakage test is like a whole building test in that you have one big zone with all interior doors open, except the tested unit has a blower door installed. By having this blower door there, it creates a small pressure difference between the tested unit and the main body of the building, and then you cruise that fan at 0 pascals reference to the main body, and the measurement of that fan gives you your exterior leakage. In addition to the exterior leakage, we also wanted to measure leakage across the common walls to adjoining units. In order to do this, we first performed a normal guarded test, meaning adjacent units were open to the main body of the building, so that adjoining units were actually guarded against the tested unit, giving us only our exterior leakage. But then our second step was to close these adjoining unit doors and open a window to outside. So now all we were guarding is the wall along the hallway. So our measurement through our tested unit's blower door was now including leakage from exterior, but also leakage through the common walls because they were open to outside from the open window. We did our testing this way so that we could actually break out the total unit leakage into 3 leakage locations: exterior leakage, leakage to adjoining units, and leakage to common space. Our compartmentalization test gives us the total leakage for the entire unit. The guarded unit test gives us the leakage to exterior. The total leakage minus the exterior leakage gives you the interior leakage, both to common space and adjoining units. The guarded unit test with the adjacent unit windows open gives us exterior plus adjacent. Total minus exterior plus adjacent gives you leakage just to the common space or hall, and exterior plus adjacent minus the exterior leakage gives you just adjacent leakage only. Like I mentioned earlier, we only had a few garden-style buildings tested in this study, so the following results are all from the common entry buildings. These buildings were spread across 6 states. We had 10 in Minnesota, 4 in Illinois, 3 in Iowa, and 1 in Michigan, Oregon, and Washington each. Most of these buildings were 3-story buildings. 2 of those were actually 2 residential floors over commercial space, the 2 mixed-use buildings I was talking about earlier, and we also had 1 2-story building. An average of 31 units with a minimum of 6, maximum of 60, and an average floor area of 33,000 square feet, minimum being 6,700 and maximum being 72,700. This histogram shows the results of the total building leakage in ACH 50. The average for the whole study was 1.54 with a median of 1.3. Minimum being 0.41, which was actually a passive house that was tested as part of this study. That came in at 0.41. The max was 3.25. State averages, Minnesota came in at 1.19, Illinois at 1.47, however it would be 1.82 if you weren't accounting for the passive house. Iowa came in at 1.63, Michigan at 1.89, and Oregon and Washington a little bit higher at 3.16. This bar graph shows the same ACH 50 results. Notice most of our buildings fell between 1 and 2 air changes per hour, with a few outliers, the passive house, and our leakier buildings out in Washington and Oregon. I mentioned earlier that one of the goals of the study was to determine if there's any building or design characteristics that could help predict the envelope leakage of a building. The initial characteristics that were considered are code requirement and enforcement, if the building is following some type of national program such as Energy Star, and if that program requires blower door testing or a target. What type of ceiling or roof the building has. Is it flat or a vented attic space? Space below the lowest level, such as slab on grade, garage, basement, commercial. The air barrier approach for exterior grade walls, the demising walls, air ceiling details between apartments, again, the type of ceiling or roof, and whether or not the building was a common entry or garden style. It turns out that the code requirement and attic type explained about 80% of the variation in leakage. Vented attics actually had 0.7 ACH 50 leakier than flat roofs. The buildings with vented attics, shown in red, were all leakier than the flat roof buildings tested within the same state, and in general were just higher overall. With the exception of Illinois and Washington, which had quite a big variation in test results, there was a general trend that areas with tighter code requirements ended up having tighter building results. Although most codes and some programs' requirements are listed in ACH 50 for target air leakage, some programs such as Passive House and even Energy Star are starting to have requirements listed in CFM 50 per square foot surface area. This histogram shows the distribution of test results listed in CFM 50 per square foot surface area. On average, the buildings were about 0.2. Median was 0.19. The minimum was the same passive house in Illinois at 0.05, and the max was 0.38. The state averages look pretty similar to those listed under ACH 50, with Minnesota at 0.17, Illinois at 0.18, and 0.22 without the passive house. Iowa comes in at 0.24, Michigan at 0.28, and Oregon and Washington once again coming in at 0.32. At first glance, the distribution of the buildings shown in this bar chart looks similar to that for the ACH 50. However, you'll notice that some of the buildings are not in the same order. So this Illinois building was actually not the leakiest in terms of ACH 50. So can we really use the two interchangeably? The answer is no, we cannot. If you're familiar with testing single-family buildings, you may have noticed that larger houses seem to test better than smaller houses, even if it's the same builder and same trades building each building. The reason for this is the ratio of volume to exterior surface area is not constant, especially when you start looking at buildings less than 25 units. The ratio is much lower and far less consistent than buildings with more units. Because of this, a smaller building with a higher ACH 50 might actually have the same or better CFM 50 per square foot surface area as a larger building with a lower ACH 50 result. Moving on to some of the results from the individual unit leakage, let's start by comparing some of the exterior and total leakage. Both of these charts show individual results from each unit test. The green circles show exterior leakage and the blue diamonds show total leakage for each unit. At first glance, the chart on the left might suggest there's a nice relationship between exterior and total leakage within the units that we tested. However, for this chart, the results were sorted separately. The chart on the right has each unit's total leakage paired with its exterior leakage measurement. And as you can see, the results are not very consistent. If you look at the units that tested around 1 ACH 50 for exterior leakage, the range of total leakage varies from 2 to almost 6, and even tighter buildings that have very little exterior leakage can have ranges from 2 to even 4.5. This box plot shows how much variation there can be between the exterior and total leakage, even within a single building. If you're unfamiliar with a box plot or box and whisker plot, these black lines represent the median for the data set, and above and below that is 25% of the data points, and each whisker is 25% of the data points. So the buildings down here not only had smaller exterior leakage as percent of total, but they were much more consistent in their results. Buildings with larger boxes had much more variance. This box plot shows the results for a single building broken out by floor level. You'll notice the top floor is not only leakier, but has a lot more variance. That's because this building had a vented attic. These two charts show a breakdown of per unit basis exterior versus interior leakage. The blue bars represent the exterior leakage, red bars indicate interior leakage, and the yellow diamonds indicate the percent of exterior leakage. If you're guessing that the building on the left is the building with the vented attic, you would be correct. This box plot shows all of the tested units broken out by vented versus unvented and also by floor. Notice that the variation in top floor vented attics did normalize a bit as compared to looking at a single building. However, it is still significantly higher than the lower floors in both vented and unvented. So if you're trying to use a compartmentalization test to estimate the exterior leakage of a unit, if you're on a middle floor or lower floor, it's maybe safe to assume that you're going to be in around the 25% range. However, if your building has a vented attic and you're on the top floor, you're going to want to assume a much larger percentage of that is leakage to outside. Because of the extra step we took to open windows in adjacent units during our unit exterior leakage test, we're able to further break out our interior leakage into common and adjoining. The black points on this chart represent the interior leakage. The green points represent exterior leakage. As we've already discussed, the interior leakage for most of these units is either higher or much higher than the exterior leakage. And by further breaking out this interior leakage into the yellow points here, which is common space or hallway, and red points, which is adjoining units, we can see that there's actually a trend to have more leakage to common space than there is to the adjoining units. This was a bit surprising because most units have more surface area shared with adjoining units than they do to common space. Typically, it's just one wall along a hallway. Although we did not have the time to fully investigate this, one thought we had is that the interstitial spaces between units, both the firewall and the floor cavities, both floor and ceiling, are actually better connected to the common space than they are to the adjoining units. So once air is lost from the unit, it's more likely to find its way to common space than it is to go through those spaces into the next unit. Another thing we wanted to look at as part of this study is whether or not the ratio of exterior to total surface area could be used to predict exterior leakage from a compartmentalization test. And unfortunately, the answer is not really. The red line here indicates a one-to-one relationship between the computed or estimated leakage and the measured leakage. If everything lined up, we would see a lot more points on this line. The blue dots, however, which represent the bottom level, are overestimated. These orange dots, which represent the middle level, are actually underestimated, and the gray dots representing the top level are kind of all over the place. This chart shows the same information from the previous slide, except shown as a percent error from the computed leakage. Once again, this zero line is our target, so if this was a good means of predicting exterior leakage from a compartmentalization by using the ratio of exterior to total surface area, we would hopefully see a lot more dots along this line. However, once again, we're seeing more blue dots for the bottom level being overestimated, more of the orange dots for the mid-level being underestimated, and kind of a scattering for the top floor. As I mentioned earlier, we actually went against most recommendations for compartmentalization testing by keeping adjacent units closed and measuring that pressure rather than having those doors open. Although it is still best practice to have the adjoining units open for the most accurate of tests, we found that it really doesn't change the overall measurement too much. First of all, the chart on the left shows that a significant majority of our units tested below the 5 Pascal pressure threshold we set in order to repeat the open door test of the compartmentalization testing. The chart on the right shows that even when we did exceed that 5 Pascal limit, it wasn't really until we got to the 10 Pascal range that we saw a significant increase in leakage. This 1.1 is actually a 10% line, so everything that was around 10 pascals or less was only changing about 10% when we did the second open door test. So if you find yourself testing an occupied building where it maybe isn't easy to open all adjacent units at the same time, as long as you can stick a pressure probe underneath the adjoining unit doors and measure the pressure, and if it's less than 5 pascals, you can probably consider your test to be fairly accurate. The final point I'd like to make is common area leakage versus unit leakage in terms of the whole building ACH 50. We found that in the buildings we tested, there's a lot more common space leakage than residential unit exterior leakage. Over here we see the common area, and down here the residential area. This line is a 1-to-1, so only 3 buildings actually tested tighter in the common space versus the exterior leakage of the units. This dashed line here is actually a 2-to-1 ratio, so nearly 8 buildings were twice as leaky from the common space versus the unit exterior leakage. So although this means that we're probably seeing good air sealing details within units and therefore good energy performance within the units, the buildings as a whole could use some improvements through air sealing details to the common space. So finally, I'd like to just leave you with a short summary and some main takeaways. On average, the buildings we were testing came in at 1.54 ACH 50, which is 61% below the codes for each state that they're tested in. And relatively, these buildings are tight. One ACH 50 90-unit apartment building can be tested with only 3 blower door fans. That's something one person could easily do. Code leakage requirement and attic type explained 80% of the variation in leakage that we tested. The floor level had a big impact on how leaky a unit is and where the leaks are located. Remember, vented attics were substantially leakier than all the other units that we tested. When using an exhaust-only ventilation strategy, where is that air coming from if only 20% of the leakage is to outside? Something to consider for balanced ventilation recommendation. And remember, don't forget the common spaces in air sealing details on multifamily buildings. If you have any questions, feel free to contact Paul or myself. Our emails will be on the next slide. Thank you for watching our presentation on multifamily test methods and results. We'll talk to you next time.